Hi everyone. This is the first of two lectures on the two-state paramagnet and negative Kelvin temperatures. So in this first lecture, I'm going to introduce you to the concepts behind the idea of negative Kelvin temperatures in this system. And in this next lecture that I'll post on the subject, we'll go more into the math behind the two-state paramagnet and develop expressions for the potential energy as a function of temperature and then derive the heat capacity as a function of temperature for this system. Okay, so first, before we get really weird, because this is some really weird stuff here, I want to remind you of some previous ideas that we developed on the two-state paramagnet. Now, I do have other lectures posted on the thermal physics channel or the thermodynamics channel on these topics, so if you want to go back and watch those first, you might know a little bit better what's going on, but we'll do a review here. So, a lot of these ideas are rooted in classical physics. Remember that if you have a magnetic dipole, symbol for that is mu here, the vector mu, and you place it in an external magnetic field, then that magnetic dipole will feel a torque that rotates it to try to align it with the external field. This is exactly the idea behind how a compass needle works. Your compass needle is a little magnet, and then when you place it in the external magnetic field of the Earth, or near any other big magnet, by the way, it'll rotate and align with that external field. Now, there's a potential energy associated with the alignment of a magnetic dipole in a magnetic field. That potential energy expression is U is equal to minus mu dot B, where yet again mu is the magnetic dipole moment and B is the external field. Now the minus sign is because if the dipole is oriented parallel to the field or with the field, then that's the lowest energy state that it can be in, right? It's aligned, it's happy, there's not going to be any net torque anymore. However, if the magnetic dipole is oriented anti-parallel to the field, so that it's pointing in the opposite way, then that'll be the highest energy state for that system, okay? And so that's why the minus sign is there. Now, this is for a classical dipole, okay? For a classical dipole, it could be at any particular angle with respect to the field. But for a quantum dipole, like, say, for example, a magnetic moment of a nuclear spin system, or the magnetic moment of an electron, then there's going to be a limited number of states. So specifically for a proton, for example, particles are either spin up or spin down, okay? And this means that for a quantum particle, they're as aligned as they get with the field. Now, you can't know exactly how aligned it is with the field because of the uncertainty principle, but that's a different lecture. So just take it for now that you can either be as aligned as you get with the field or as anti-parallel as you get with the field. And that is our classic two-state paramagnet. Now, in a real system, you could have more states than just two. You can have a magnetic spin that's a number of integer states, an odd number of integer states. But for this two-state paramagnet, we're just going to consider spin up and spin down particles, which means that it's either spin up aligned with the field or spin down anti-parallel with the field, okay? All right, so according to our potential energy expression, U is equal to minus mu dot B, then that means that there's going to be two energy states. Now, if you consider it to be perfectly aligned, which it's not, but just consider it to be perfectly aligned for a second, then that would be U is equal to minus mu B for the up, which is parallel to the field state, right? And if it's anti-parallel to the field, then U would equal mu B, okay? And this is, of course, surrounding U is equal to zero, the zero energy state, okay? So that's that. Now, if you have a collection of dipoles, let's say that you have n total dipoles, then those dipoles, if there's only two states, would be split between the spin up and spin down states. So if we call n the total number of states, then let's have n with the up arrow indicate spin up particles, the number of spin up particles, and n with the down arrow indicate the number of spin down particles. And n would be equal to n up plus n down in our simple two-state paramagnet, okay? Now, in some of our previous lectures on thermal physics, we drew an analogy in between our two-state paramagnet and coin flipping, okay? So if you flip a coin, you get heads or tails. If you flip a two-state paramagnet, it'll either be spin up or spin down. So that means that you calculate the multiplicity for a two-state paramagnet similarly to how you calculate the multiplicity for coin flipping. And that gives us our expression for the multiplicity here. If you look at some collection of n dipoles, right, and you know the total number n, and then you look at the multiplicity for how many of these, how many ways can we arrange the system. I have 100 spin-up dipoles, for example. Then omega for n up would be equal to n factorial divided by n up factorial divided by n down factorial, okay? And we developed this expression in a previous lecture, okay? Now, if you're trying to calculate an entropy from a multiplicity, you just use the equation S is equal to Boltzmann's constant K times the natural log of the multiplicity, all right? So, from knowing the multiplicity of the number of ways that you can arrange having, 100 spin-up particles, you can calculate an entropy. Now, let's also think about what the total energy of a system would be that has n dipoles, with n up being the number that they have up and n down the number that they have down, okay? So if we accept the premise that the energy of a anti-parallel particle is mu b, and the energy of a parallel particle gives you minus mu b, then your total internal energy for the system would be mu b times n down minus mu b times n up. And that would give you your total energy for your two-state paramagnet system. Now what you can do is plot the entropy versus the internal energy. Now I've done this. I have an Excel file here. Let me show you. What I did was I just had a system of 100 two-state paramagnets. And then I said, okay, what's going to happen? What's my multiplicity if all of them are parallel with the field, all the way to all of them are anti-parallel with the field? Okay, and then I calculated the entropy with respect to that multiplicity that I calculated, and then I plotted it S over K, S over Boltzmann's constant, versus the internal energy over mu b. Okay, so that's what I've done, and that's what's shown here in this graph on the right. Okay, plotting S over K versus U over mu b for a system of 100 oscillators. And then I just allowed the number of up spins to vary from 0 to 100. Okay? So, looking at this plot, I think it's relatively straightforward to understand what's going on with the entropy and the internal energy. If you have, for example, all of the particles being aligned with the field, right? They're all perfectly aligned with the field. Then that would mean that all of the particles are in their lowest possible energy state, okay? Now, that would be over here on the left, right? Over here on the left. And the number of ways that you can have all the particles being spin up, for example, would be 1, which makes the entropy 0, okay? Fine. Now let's go all the way here to where you have a total internal energy of 0. That means that half the particles are spin up and half the particles are spin down. And n down equals n up, and so this u here goes to 0. Now, that would also correspond to your largest multiplicity. We've kind of talked about this before, right? You get your largest multiplicity and your largest entropy when it's evenly distributed, right? So that's our max entropy. Now, go over to the far right-hand side of the plot. Over here, you have an energy where all of the spins are anti-parallel to the field. So all of them are in their highest energy state. So that would give U is equal to mu b times n, right? The highest possible energy state. Now, that corresponds to a multiplicity of 1, because there's only one way to do that, which corresponds to an entropy of 0. So that's why the plot looks the way that it does. Okay, so that part of it is pretty straightforward to understand, okay? And you can conceptualize it too by saying, okay, well, if they're all over here in their lowest energy state, usually we think of that as cold, right? If everything's in its ground state, it's really a cold system. And if everything is in its excited state, then it's hot, okay? So left cold, right hot. So that would be how we would interpret it, right? All right. Now, we have spent a few lectures before now talking about the true definition of temperature. And the true definition of temperature comes from this partial derivative. The partial of the entropy with respect to the internal energy, holding the number of particles in the volume constant, is equal to 1 over the temperature, okay? So there's that. Now, what that means is that the slope on an entropy versus potential energy graph can give you the temperature, right? Because derivatives are slopes. So, if we have a positive slope, as we have for u less than 0 here, then that would mean that we have 1 over T is positive, and we have a positive temperature, right? But now, here's the weird part. If u is greater than 0 here, if it's on the right-hand side of this plot, then the slope is negative, which means that the partial of s with respect to u is negative, which means that 1 over T is negative. Now, I'm not talking about negative Fahrenheit or negative Celsius here. We're used to that. That just means it's cold. What I'm talking about is a negative Kelvin temperature, okay? So, that would mean that for this system, which we've developed and which we thought we understood, there's actually a little something going on, and it's that you've got a negative Kelvin temperature there on the right-hand side of that plot. So, can something get lower than 0? I mean, what does that mean? We already said that the left-hand side was cold and the right-hand side was hot. What? Okay, so that deserves a second. Maybe you should pause the video and just ponder that for a minute. Now remember that this is completely counter to the S versus U graphs for some of the other systems that we've already developed and talked about. On the left is a normal system, the ideal gas, and remember that the Einstein solid looked a lot like this plot. Now plots like this one result in positive Kelvin temperatures. Yay, right? And they also result in heat capacities that are constant and positive. So this is normal life here on the left. We also talked about black holes, okay? If you plot the entropy versus the internal energy for a black hole, you get a positive slope, at least, thank heavens, although there is fallout, okay? So for this system on the right, remember, for black holes, you had an increase in the internal energy leading to a decrease in temperature, which means that you have a negative heat capacity and one that's, by the way, not constant. But at least it's a positive temperature. So it's weird, but at least it's positive. This is a negative Kelvin temperature. So what's that mean? All right, so let's think this through. Now you might be saying, okay, this is all nice, but she's kind of nuts, and this couldn't really happen. But the thing is, it does. Here's some citations from a couple of papers. One of them's from 1950, and it's entitled A Nuclear Spin System at Negative Temperature by Purcell and Pound. Okay, so this is an experiment where they actually created this system. And then the one here on the bottom is some analysis of what that would actually mean from the thermodynamics and statistical mechanics at negative absolute temperatures. And that one's by Ramsey, and it was published in 1956. So this is documented. This is real. There are negative Kelvin temperatures. Okay, I'm not making this up. You can Google it. So what did this experiment do, this Purcell and Pound experiment? Okay. So, the Purcell and Pound experiment of 1950 looked at the spins of lithium nuclei in a lithium fluoride crystal. Now, what they did to give the system a negative Kelvin temperature experimentally is actually relatively straightforward. They took this spin system, okay, and they placed it in a strong magnetic field, a strong external magnetic field, right? That caused most of the dipoles to align parallel, or as parallel as they get because they're quantum particles, to the field, okay? So we had an aligned system. Then they flipped the direction of the external magnetic field to point the opposite way. When that happened, that meant that most of the collection of nuclear spins were anti-parallel to the field, okay? So we had spin systems aligned anti-parallel to an external field, which, remember, is what got us into this negative Kelvin temperature thing in the first place. They were in that excited state where they were anti-parallel to the field with a positive U, but a slope on an S versus U graph that was negative. Okay. All right, now, what happens is that, and maybe I can show you, I'll show you here. What's on this plot on this left-hand side, if you can't read it, I know the type is small, is a record of the nuclear magnetization. So this is plotting the magnetization of the sample versus time during the experiment, okay? So on this left-hand side right here, this is a magnetization that is in the net negative direction, which would mean, of course, parallel to the field. And then on the right-hand side, they flipped it, and now they have the positive magnetization, okay? And so what they say here in the caption is that when it's the normal state, that corresponds to like 300 Kelvin, for example, room temperature. And then when it's in the other way, then you've got a negative Kelvin temperature. They cite from the slope of their graph, negative 350 Kelvin. So this is something that's actually been documented and shown, and this is the magnetization curve. Okay, so if you know the magnetization, then you know the number of spins parallel and anti-parallel to the field. So for example, the magnetization, the net magnetization vector for a system of n particles would be given here. The net magnetization or total magnetization, capital N, would be the magnetic moment minus mu for it to be parallel to the field, right? Anti-parallel to the field, which would be the number down, plus the number that are parallel to the field and up times the magnetic moment for that orientation, mu. Okay, so that gives us our magnetization vector, and then that's equal to minus u over v, okay, from our previous equation for the internal energy of the system. So if you have the magnetization vector, then you can very easily calculate that internal energy of the system, okay? Now, from the magnetization, if you know the total number of particles, you can then figure out how many of them are spin up and how many of them are spin down from that magnetization. If you know that, then you can calculate the entropy of the system from the equations that I showed you previously. Then you can extract the temperature by finding the slope on that S versus U plot at the point in question. So that's how that was all done, okay? So here we are with this negative Kelvin temperature state. So what does all that really mean, okay? Well, first of all, if you hooked a regular thermometer, okay, up to that experiment, regular thermometers are based on regular systems like solids, liquids, gases, okay? So you wouldn't get anything strange, okay, from doing that. It would still read a positive Kelvin temperature like always. Your thermometer wouldn't explode or break or anything like that. It would still just go on reading whatever the temperature was before you flipped the magnetic field, probably, okay? And everything would seem normal. And that's because regular thermometers are based on regular systems, and regular systems don't have S versus U plots that look like that. They have S versus U plots that look like this one on the left, where there are no negative Kelvin temperatures. So, in terms of your everyday experience, what happens at a negative Kelvin temperature, this is the temperature of the nuclear spin system, okay, which is not the same as the temperature of the crystal, all right? That's a different question. Okay, so for one thing, I want to reassure you about that, okay? Now, that doesn't change the fact that due to our true definition of temperature, partial S with respect to U is 1 over T, holding N and V constant, that we don't have a negative Kelvin temperature for this nuclear spin system, okay? So we still need to figure out what the heck that means, what it means to be cold or hot in that system, and try and interpret a little bit what's going on. So let's give that a shot. So to do this, let's think about the slope on this S versus U plot and figure out what it means at various points. Okay, so I'm going to start over here on the left where things are normal and work my way over to the right where things are very strange. So for U is equal to 0, or for U is less than 0, I'm sorry, on the far left-hand side of that plot where it intersects S equal to 0. if you look at the lowest possible energy state, this was just for a collection of 100 dipoles. If you increase to a normal, regular number of dipoles, you'd have a huge number, like 10 to the 23rd dipoles or something like that. If you did that, then that slope on the far left-hand side of the plot would get steeper and steeper and steeper. So basically, it's approaching, that slope is approaching straight up and down, which would approach a slope of positive infinity, okay? Now, if a positive infinity slope is equal to 1 over the temperature, then remember, that means that the temperature is approaching positive 0. Yes, I said positive 0. Basically, what I mean is on the left-hand side, you have positive slopes. Okay, so that's what I mean by positive 0. I'm referencing our normal temperature scale here. Okay? Now, that kind of makes sense based on what we said before. If everything is in our lowest energy state, then that means that the system has got to be cold, and 0 Kelvin is as cold as it gets. So if it's approaching our regular old 0 Kelvin, and it's in the lowest energy state for a huge collection of dipoles, that kind of makes sense to me. Okay, now, as you increase the internal energy U, but stay on the left-hand side of that plot, then you'll have some positive finite slope, say here at this intermediate spot right here, okay? That's some positive finite slope. And so from that positive finite number, you could set that positive finite number equal to 1 over T and solve. And hey, maybe you even get something normal like room temperature, 300 Kelvin, okay? So that's what you get there in the middle of the left-hand side. Now let's go to the middle of the plot, which is the tip top of our S versus U curve. What's the slope at the top? Well, that's an inflection point, right? It's going from, you know, a positive to a negative slope. So right there in the middle, the slope is 0, okay? So at U is equal to 0, if we're approaching from the left, then that means that 0 is equal to 1 over the temperature, which means that the temperature approaching from the left, right, that's a positive slope approaching from the left, the temperature is approaching positive infinity. So as it gets to that point, the temperature is positive infinity of this nuclear spin system. So that's a little weird, okay? But that just means that, you know, U is equal to 0 just means that it's half up, half down spins. Okay? Okay, so that's the left-hand side. Now let's look at the right-hand side, which is a lot stranger, okay? Let's say that we're at U is equal to 0, but we're approaching it from the right-hand side, okay? That means that we have a negative slope, but it's getting shallower and shallower and shallower. So approaching from the right, 0 is equal to 1 over T, but the slope is negative, so T is approaching negative infinity. Okay. Now, at an intermediate point, okay, say here, okay, then you have a negative finite slope, and 1 over T is some then negative finite number, so T is some negative finite number, like negative 300 Kelvin. Then on the far side, where everything is in the highest energy state, right, you've got almost a straight up and down line too. But it's going to be a little off, so it'll be kind of negative straight up and down. So that means that your slope approaches negative infinity, which is equal to 1 over T. And so that means that T is approaching negative 0. I didn't make this up. So, if we were to plot an energy, or I'm sorry, a temperature scale, thinking about cold being on the far left and hot being on the far right, then our temperature scale going from cold to hot would be positive 0, positive 300 Kelvin, positive infinity, negative 300 Kelvin, negative 0. And so negative 0 would be as hot as you could get. And positive infinity would be intermediate between positive 0 and negative 0. That would be what your temperature scale looks like. So negative infinity Kelvin is actually hotter than positive infinity Kelvin in the normal way of thinking about what hot and cold is. So, according to Ramsey, who published that paper in 1956, I'm going to quote him, With the above definition, if two systems at different temperatures are brought into thermal contact, they will reach some final temperature which is intermediate between the two starting temperatures. It should be noted, however, that positive 1000 Kelvin is intermediate between positive 300 Kelvin and minus 300 Kelvin. That's what I just said. Wow. So that's strange. So that's the kind of math of the slopes. So what does that mean? Well, according to Ramsey, the definition which agrees best with the normal meaning and which will be adopted is that the hotter of the two bodies is the one from which heat flows when they're brought into thermal contact, while the colder is the one to which heat flows. And with this definition, any negative temperature is hotter than any positive temperature. In other words, if the spins are anti-parallel to the field, that's a hotter state, and they're going to want to give energy up to a system where the spins are parallel with the field, right? That's the deal. So let me reiterate. If you hooked a thermocouple or something up to this lithium fluoride crystal, you wouldn't get anything weird. The lithium fluoride isn't changing its temperature all that much during the experiment, and you wouldn't freeze or burn your fingers if you touched it. The negative temperature is the temperature of the isolated spin system, and according to Ramsey, I'm quoting, 10 to the 12th seconds would be required for appreciable amounts of heat to diffuse 1 centimeter in a crystal if the only mechanism for thermal diffusion were the nuclear spin system. So in other words, this isn't really a typical temperature that we're thinking of. This is the temperature of the nuclear spin system, okay, itself. And this mechanism of heat transfer does not dominate, okay? The normal mechanisms dominate. Remember that 10 to the 12th systems, there's pi times 10 to the 7th seconds in a year. So this is a really long time, okay? 10 to the 12th seconds is a really long time. So as to what all this means, systems with negative temperatures are really happy to donate their energies to systems with positive temperatures. They're trying to get back to a higher entropy state. And to do that, they have to donate energy, not receive it like normal systems. So, yet again, the entropy is really the fundamental quantity here, not the temperature. Temperature is just a way to measure how a system responds to changes in entropy with respect to internal energy. And that was really getting at the root of our definition for the true definition of temperature. Okay, now I'm not going to say that that wasn't confusing. It really is, okay? But I hope that it provoked some thought, that it got you excited about thermodynamics, because honestly, I think this is pretty cool. It's as cool as thermo gets, really, and I hope you enjoyed it. I'll see you in class.